Well, thank you very much, Paul, and it's a pleasure to have the opportunity to speak to you today. This talk will be about the role of computing, particularly high-performance computing, in developing models, not just in chemistry, but in other areas, because the ability of computers to develop accurate and increasingly reliable models for complex systems has been one of the major developments in science in the last 30, 40 years. It's a recent development, but it's a recent development that relates to one of the oldest of scientific activities, and that is model building. Because model building is as old as scientific thought. What I'm showing you here is the Ptolemaic model of the universe, a very beautiful model. This is a real physical model, just an illustration here. Developed in the ancient world, and a successful model. This model helped to rationalize many of the astronomical observations that were available in the ancient world. And of course that model was swept away by the heliocentric Copernican model in the 16th century. But it illustrates the fact that scientists have needed models since the very beginning of scientific thought. So these are areas in which we use computers to build models. It's not an exhaustive list, but it illustrates how broadly computational modeling is now used in science. Cosmological modeling, absolutely key area of contemporary cosmology, not an area that I have expertise in. Atmosphere, ocean and climate modeling. A great deal of what we are predicting about the evolution of the Earth's climate derives from sophisticated computer models. Geophysical models, I'll give you an example in a few minutes. Aerodynamic modeling, absolutely key to the aviation industry. Epidemiological models, again, absolutely vital in the field of public health. And then my own speciality that I'll speak about later on, the development of models for molecules and materials. So what do we do in computer modeling? Well, it's an interesting kind of conceptual area. We use very basic scientific knowledge, for example, gravitation, our knowledge of gravitation, quantum mechanics, which is the basic knowledge of how electrons behave in atoms and molecules. Hydrodynamics, we'll give examples later on. So we use this basic knowledge to construct models, convert complex real systems. And you can think of it as the converse of reductionism. Reductionism was an absolutely key discovery, as it were, in scientific thought. The idea there is you strip nature down to its very essentials and pick out the fundamental underlying principles. Science has been very successful in that respect, so we can now use these fundamental underlying principles with the immense processing power of computers, as I say, to construct models of complex real systems. And so it's an integral part of contemporary physical, biological, medical sciences and engineering, as my previous slide showed. So what's the motivation? Well, the first motivation, model building, I've already discussed. Scientists need models to help them understand the complex systems which they're attempting to, whose behavior they're attempting to fathom. So model building, very, very broad, general need. But here are some more specific ones. Computer models can be very valuable sources now of numerical data. For example, a great deal of what we know about impurities, defects in semiconductors that control their behavior, key materials in the contemporary world, comes from computer modeling. Inaccessible systems, I'm going to give you an example in a few moments of beautiful applications here from UCL of computer modeling, helping us to understand the Earth's core, which most certainly is an inaccessible system. And then perhaps most ambitiously, we use computer modeling to predict new systems and phenomena. And again, I hope to give you an example later on. So we're going to have some grand challenges. UCL is a great place for grand challenges. Here are four, not the UCL grand challenges, but the grand challenges that I'm going to discuss in a few moments. We're going to look very briefly at how computers are being used to model star formation. We're going to come down in length and time scales. Then we'll look at modeling the Earth's core that I've already referred to. Then modeling turbulent flow, key area in engineering. And then at the end, my own speciality of modeling materials at the molecular level. Well, let's just look pictorially at the first challenge, modelling star formation. And here I'm going to highlight fantastic work from Qinhua Wu from our Department of Space and Climate Physics at UCL. And essentially what we're doing here is applying hydrodynamics at the galactic scale. And I'll just show you a couple of images. In fact, these were supposed to be movies, but in some ways they're more effective as single images. And what these are showing are the early stages of condensation of a gas cloud of galactic dimensions into stars. So that's it. The scales here in length and time are enormous, but this model gives us insight into the early stages of this condensation process. I could show you lots of examples here of these beautiful images. This is another one where after which essentially a jet of gas has come from the center of the galaxy, and again we're beginning to see this condensation into star formation. Talk to Qinhua if you want to learn more about this fantastic area, but it's showing you modeling here is getting to grips with this, as it were, cosmological, astronomical event would be more accurate. Now let's go on to my second example, and we'll come down a little bit in the length scales here to modeling the Earth's core. And again here I'll be highlighting fantastic work here at UCL, Dario Alpha, Mike Gillen, David Price and Lidunka Catlow in the Department of Earth Sciences. Now what they're doing here is they're applying quantum mechanics to allow us to understand key aspects of the behavior of the Earth's core. Quantum mechanics, as I said, is the basic theory of how electrons behave in atoms, molecules and solids, and they're applying this knowledge with the help of enormous computer processing power to help us, I say, answer key questions about the Earth's core. This is part of a larger program led by Dario Alpha, joint between the Department of Earth Sciences and Physics, applying quantum mechanical techniques to study materials under immense conditions of temperature and pressure. So let me remind you a kind of kid's model for the structure of the Earth, which I think probably most of us know. The Earth in the center has the core, and that's got two components. The inner core is solid metal, mainly iron. The outer core is liquid. Then surrounding the core we have the mantle, which is predominantly silicate minerals. And then right on the top, as it were, is the crust, the rather thin crust on which we all live. The other point that this slide is making is the way in which seismological data has been used to probe the structure of the Earth. Now, we've known that basic idea, the basic features of the structure of the Earth for a long time. We've also known from a number of pieces of evidence the composition of the core. The evidence comes from cosmic chemistry, distribution of elements in the cosmos, analysis of meteors, equations of state, learning from seismology the properties of the materials at various parts in the Earth. And we know that, as I said a few minutes ago, that the core is iron, alloyed with a small fraction of lighter elements. Now, why is the core important? It's important for a number of really very significant reasons. It's the seat of major global processes. The core, as we'll see in a few minutes, is extremely hot, and the heat coming out from the core drives the convection in the mantle, which is responsible for plate tectonics, which certainly influences, as we know, dramatically what takes place on the surface of the Earth. One other important feature of the core is that convection in the outer core, the liquid part, generates the Earth's magnetic field. And the Earth's magnetic field is certainly more than a curiosity. I love showing this slide. The Earth's magnetic field has an absolutely vital role in making life on Earth actually possible. What we're seeing here is a solar wind. Again, this is a picture that was provided for me by NSSL. A solar wind coming out. It's an illustration, but the point we're making here is that the Earth's magnetic field protects the Earth from the consequences of that solar wind. So the Earth's core knowledge of the Earth's core really is very important. Now, the problem which Alpha and colleagues addressed was the temperatures. So absolutely key quantity that we need to know, the temperatures at the inner outer core boundary and then the outer core mantle boundary. Those are absolutely vital knowledge for contemporary geophysics. And they use this very sophisticated quantum mechanics to work out the melting points of iron under the conditions of huge pressure that we know are present in the Earth's core. They measure the melting point by finding the regions at which liquid, which is on the right there of this graphics, and solid coexist. So via this very sophisticated procedure, they're able to determine the melting point of iron under these huge conditions of pressure in the Earth's core. And to cut a long story short, this was the model that they derived for these key temperatures at the inner outer core boundary and the boundary of the outer core and the mantle. So that is key knowledge for geophysics. And as I said earlier, this is an inaccessible system. So this really is an absolutely vital method for deriving this essential knowledge. Now, this work has been going on for quite a long time, and what I'm going to show you now is a headline from the Daily Mirror after one of the earlier papers was published in the journal Nature in the late 1990s. And they were greatly taken by these predictions as to the temperatures of around 5,000 degrees, which are the same temperatures, as, I think, as the surface of the sun. And so they came up with this wonderful headline, Core Water Scorcher. So I would say that was the Mirror, October 1990. Now that's actually, I think, perhaps the first time that results of a computer modeling exercise, certainly in science, have got a full page spread in the Daily Mirror. Anyway, let me go on to my next theme, and I should say here I'm a long way on this next one from my own expertise, but I'm highlighting some work that was provided me by Ian Eames, many other colleagues involved, from the Department of Mechanical Engineering, really just to emphasize that computational modeling is a really key technique in contemporary engineering. And they're concerned with fundamental fluid mechanics. So we need to understand, for instance, how fluids flow around complex shapes. And this can be, I'm sure, as you all know, highly complex. Lower down we have an example of turbulent flow, an extremely important phenomenon, and one that is actually very difficult in many ways to get to grips with quantitatively. Now, they are doing fantastic computational work, but the best computational work, whenever it can be, is tied in with experiment. And so they're also doing experimental studies using this new fluid mechanics laboratory, again, of the way in which complex flows occur around objects. And I'm just going to show you, so it's outside my area of expertise, but 3 examples of work of this group. This is, I thought, an absolutely wonderful one. This was modeling of the breaking of a tsunami. You can see the graphics on the right-hand side. Obviously highly topical in view of the tragedy there was a number of years ago when the tsunami in the Indian Ocean. And they're able to model this really rather accurately. They can model the breaking of the elevation wave, and very importantly, their models predict this very extensive backflow that you see here, which is one of the major problems observed in the Indian Ocean tsunami. So then please talk to Ian if you want to learn more about this. But then just illustrating the diversity of their work, here is a summary of, again, a very extensive study applying modeling to airborne transmission in hospitals. As you all know, a very important phenomenon. They're able to model this really quite accurately, and the results are providing guidance to reduce infection spread. And if we want to go to an even more medical application, here's work that they've done in collaboration with the Moorfield Eye Hospital concerned with retinal detachment, which is treated by replacing the vitreous medium in the eye by this gas liquid tamponade. And you need to know, again, the fluid flow properties of that fluid. And again, they've modeled that successfully and made a real serious input into this important medical problem. So absolutely terrific work, again, here at UCL. So the remainder of this talk, I'll kind of come back to home for me and discuss modelling materials, which is my own speciality at the molecular level. Now here I'm going to highlight the work of a number of colleagues in the chemistry department at UCL. And what we're doing here, we're applying quantum mechanics that I've already alluded to, and also an area we call molecular mechanics, I'll try and explain in a minute, to understanding and predicting structures and properties of complex molecules and materials. So, what do we want to know about materials at the atomic and molecular level? Well, we want to know the structures, the way in which the atoms are arranged in them. They can be arranged in a regular manner, as in a crystal, or in a disordered manner, as in an amorphous material. We want to know what happens on the surfaces. Many very important phenomena take place on the surfaces of materials, so we want to build models for surfaces and for interfaces between two types of material. I mentioned very briefly the area of defects. Solids contain impurities, imperfections, and they can often control many of their most important properties. We want to know how molecules can absorb, can fit inside materials or occupy sites on their surface. Then very ambitiously we may want to use modelling to guide us in the synthesis of new materials, understand the way in which they grow. Nanochemistry, of course, no talk on materials science can omit something on the nano theme, but a really fascinating area of contemporary chemistry. We need models for the structure of matter at the nano level, and a very ambitious area that I spent a lot of time on. I won't have probably time to talk about it. Reactivity, the way in which molecules react on solids and within their pores. And we want to apply these methods to lots of different systems, to things like oxides and silicates. Silicates are the materials that the Earth's core, the Earth's mantle and crust are made out of. We want to apply them to semiconductors. We want to apply them to molecular crystals. For example, crystals of pharmaceutical compounds. If I get time, I'll give an example there later on. And of course, a wide range of metals and alloys that we apply these methods to. Now, I don't want to kind of give you a lecture on chemistry. I just want to give you a glimpse of how we try and do this modelling in chemistry. And we use two very general strategies. The first are what I call intratomic potentials. And the idea here is, you know, that atoms are nuclei surrounded by electrons. Well, up to a point, we try and partly forget about that. We just say atoms are perhaps rather squashy spheres, and we'll develop models for the way in which these squashy spheres interact with each other. And over the last kind of 60 years, we've become very good at that. And once you've got these models for the way in which these atoms interact with each other, lots of kind of computing games you can play. You can run downhill in energy. Just say, you know you interact. Now just find the lowest energy way of arranging yourselves. You can imagine you're Isaac Newton, and you can use Newton's classical equations of motion to work out how atoms will move around given a certain amount of energy. And then you can, as I say, you roll dice to generate ensembles. You can generate lots of different configurations of your atoms and then try and calculate properties. But then the other thing you can do, which I've already referred to, you really can say, we'll use our very basic knowledge of how electrons behave in molecules and solids. Schrödinger equations summarize that, and we'll calculate these properties in detail. Well, we're back to challenges. Instead of grand challenges, we're going to have key challenges, and I probably won't get through all these, but the first will be, can we predict the structures of crystals and nanoparticles? Then we'll look and see, well, can we do some guidance for synthesis? Then a very important problem in both chemistry and chemical engineering, can we understand at the molecular level how crystals grow? And then the one I won't have time for probably is how we determine the mechanisms whereby molecules react on solids. So let's look at the first one. Can we predict the structures of crystals and nanoparticles? And we're going to start off here with a quote. This came from an article by John Maddox, who for many years was the editor of Nature. He published a very provocative News and Views in 1988, in which he said one of the continuing scandals in the physical sciences is that it remains impossible to predict the structure of even the simplest crystalline solid from a knowledge of its composition. So it's saying if you know what atoms are present in a solid, you couldn't predict their structure. Now, when that statement was made, it actually was pretty wildly inaccurate, so it wasn't terribly good science. It was fantastic journalism, though, so because it stimulated a huge response. And in fact, it was really very good because it stimulated the field. One of the earlier responses was a review by David Price and myself in Nature in 1990, in which we partly answered this provocative comment of Maddox, and then a couple of years ago, Scott Woodley and myself kind of looked at where we were following the Maddox challenge 20 years on. And the answer, the position is now we actually can do a pretty good job in many cases of predicting the structures of crystals. I'm just going to give you one or two illustrations and going to give you some of the ideas that we try and use in predicting structures. The problem is crystals are complex systems. They've got lots of atoms in. There are vast numbers of ways of arranging them. How are we going to decide what the best one is? So one approach we can use is what we call genetic algorithms. It's a really clever, neat idea, and it's based, like lots of scientific ideas are, on analogies. It's an analogy with evolutionary theories. What you say is you've got a population. You get lots of different ways of arranging your atoms, and that's a kind of population. And then you allow these populations to pass through successive generations. But the possibility of a structure procreating, passing on its features to the next generations, depends on some rough and ready measure of how good that structure is. And that's one of the key features. But I say it's a really neat idea, and in a minute I'll show you that it works. And I'm going to apply this to a type of material that I've been interested in for many years. These are systems called zeolites. They are silicates, so the basic topology is simple. They're built about a tetrahedra. You can see there, silicon surrounded by 4 oxygen atoms. Then you link the tetrahedra together by sharing corners, and then you start to build up these lovely networks. The important thing is, though, they're open networks. They can chain sheets and cages and channels. So there are lots of different structures here. We're interested in them because they're beautiful crystal architectures, but there's a great deal we can do with them. They are fantastic catalysts. That means they promote chemical reactions. I can't go into all their catalytic properties, but they're absolutely key in the petrochemicals industry. For instance, they break down tars into molecules of about the right size for petrol, so they're absolutely vital in many ways for energy security. Lots of other catalytic properties. They're also used in a very important area in industry, gas separation. These channels are about the same size as many molecules, so you can use them to sieve out, separate one molecule from another. And they are, an older example is ion exchange. In fact, a lot of them are still used in detergents. I'm going to give you one example now of a prediction of a structure using this genetic algorithm method. It isn't really a prediction, it's just showing that the method works to a known structure, soda-like. So I'll let it run again. And what's happening in the early stages, this is this genetic algorithm phase. It's playing around, finding better and better way as we go through these successive generations of organizing the atoms. Then it ends up with a very good way, and then does a kind of final push downhill in energy and generates that structure. So lots of other examples I could give you, but I want to move on to another approach. Now, this is using ideas from topology, and probably lots of people in this audience know more about topology than I do, but topology is all about the way in which different shapes relate to each other. Now, crystal structures contain complex shapes, and so for a long, long time, topology has been used to generate possible models for structures, but this process was taken one step further in very, I think, important work by Rob Bell and co-workers. Rob is now in the chemistry department at UCL. I just want to illustrate the relationship between topology and a crystal structure. With our topology on the right-hand side, you can think of it as a way of connecting vertices or a way of connecting polyhedra, but that's a kind of mathematical construct. You can turn that, as it were, into a model of a crystal structure. You put, in this case, a silicon atom at each of those vertices. You put an oxygen atom along the edges, and then it's a crystal structure. In fact, it's a crystal structure of a well-known material. Now, I can't go into any details, but I say Rob Bell and many other colleagues use this to predict entirely new structures, and moreover structures that were calculated to be stable. And this is a beautiful example of one of these new predicted structures. It's a lovely topology out of 12 and 8 rings. That is predicted to be stable. This is work about a couple of years ago. It remains a challenge to see if we can synthesize it. Just a few words later on about how we might respond to that challenge. Now, final example, again, work from chemistry department. This is work of Sally Price, Derek Tocker, and a student, Ashley Hume. And they're, again, trying to predict the structures of crystals made up out of quite complex molecules. And they use actually a rather simple idea. They systematically try and pack these molecules together in lots of different ways, and they find out the best way of doing it. And they had a really fantastic success story about 5 years ago. They very much built on that. It concerned this material, 5-fluorouracil. Now, if I get time, I'll say a few more words about that material, that molecule, in a few minutes. It's an important pharmaceutical compound. This is the crystal structure that was known for it for many years. You see here it's a molecule, and there are quite interesting ways in which the molecules fit together. That was the only one that was known. They then predicted, using their methods, that there was another way in which you could pack these molecules together in this crystal. Here it is. And that hadn't been seen before, but then in some excellent experimental work they were able to grow form 2. So that was a real prediction. They tried lots of different solvents for this, and they found that nitromethane, which is a very dry solvent, succeeded in growing that crystal structure. Now, if I get a few minutes, I'll explain how we've solved the problem of why they need this particular solvent to grow that crystal. Before I do that, a word about nanochemistry. I promised you to say something about nanochemistry. So here is some of work of my group on zinc sulfide, important semiconductor compound, and it's got a lovely nanochemistry. These are the structures predicted by kind of some of the methods I've been very briefly describing for the way in which zinc and sulfur atoms are arranged at the nanoscale. And the beautiful open structures, they look absolutely nothing like the crystal structure of zinc sulfide. And they're all open, bubble-like structures. This one on the right here is absolutely amazing. It's a big open bubble structure, so it doesn't remotely resemble the way in which the atoms are arranged in crystalline zinc sulfide. That's the way in which they would be arranged in crystalline zinc sulfide for a cluster about as big as the one I just showed you. That, our work showed, has higher energy. So the arrangement of atoms at the nano level is quite different from that which you get when you've got very large numbers of atoms in crystals. Here's an even more amazing structure. Now you've got 60 zinc, 60 sulfur atoms, and they arrange themselves in an onion-like structure. You've got a little cluster inside a big cluster. So you're getting, say, these nested onion structures. Again, nothing like the arrangement in the bulk cluster. I'll skip this one. Now, let me go on in the remaining few minutes to my second challenge. That is, can we guide synthesis and understand the factors that control synthesis? One just brief illustration. And we're going back to these zeolites, these wonderful complex crystal structures that have all these applications in industry. The way in which we synthesize them is to quite a large extent a black art. They contain silicon and aluminium, so we chuck sources of silicon and aluminium into a kind of synthesis brew. We add caustic soda, and then, very interestingly, we add organic molecules, big molecules. And what we think happens is the zeolite, all these silicons and aluminiums begin to link together, and they kind of crystallize, they grow around these organic molecules that we chuck into the synthesis jar. So some time ago, one of my colleagues, Dewi Lewis, working in collaboration with Dave Willock, decided he would try and get, this I say is a black art, but he'd try and give some guidance to it. He'd try and predict the kind of organic molecule that you needed to grow a particular zeolite structure. And he had fantastic success. He grew molecules on the computer. So he started off with something simple, like the template you see there. It's just a methane molecule. All kinds of chemical groups that then the computer starts to fit them on. It manipulates them, and it ends up with a prediction of a molecule that will sit nice and snugly inside the target material. And then you say, well, that is probably going to be a good template. And it worked. The very first example, that molecule there successfully synthesized that particular cage that I'm showing you. And here was a real fantastic success. This lovely cage here, known as Levine structured cage, we predicted by this computational method that the molecule there on the right would be really good for synthesizing it, and it worked. It synthesized it absolutely like a dream. So we can use computer modeling to guide synthesis. Now, in the remaining 2 or 3 minutes, I'm just going to look at this third challenge. Can we gain a molecular level understanding of crystal growth? Now, I should say crystal growth, one of the really big challenges in physical chemistry and chemical engineering. Now, I'm going to go back to the theme I had earlier, the work of Sally Price, but here's some contributions from Said Hamad, who worked with me. And they're concerned with this phenomenon of polymorphism. Now, the molecular crystals when you pack molecules together, often can grow in lots of different structures. There are lots of different ways of packing them together. Now, this, in the pharmaceutical industry, can be a disaster. A pharmaceutical is a solid compound. Regulatory approval only applies to one particular solid form. And what has sometimes happened during production of a pharmaceutical is that it starts to crystallize in a different form, not in the one for which it's been given regulatory approval. So this has been one of the really big problems in the pharmaceutical industry. So there's a great deal of incentive for understanding this phenomenon. Now I'm going to go back to this system 5-fluorine uracil, important pharmaceutical compound, chemotherapy for 50 years. Remind you that Sally's group predicted this new form, and there are, just very briefly to draw your attention to, sorry, I better go back, to important structural principles here. You look at that thing that I've ringed there, those are fluorine atoms close together. And just remember that. That's a feature of this form. Look at this one. You see those dotted lines, those are what we call hydrogen bonds, which are holding two molecules together. So those are the kind of two structural signatures. Now, form 1, you can grow that from water. Form 2, you only grow from nitromethane. Now, let's look at what you do when you do a simulation. You look at how the molecule behaves first in water. And you can see here this kind of greeny blue thing. That's the fluorine atom, and it's not interacting with the water. And what you find is if you have species in water that don't interact with the water, then they start to interact with each other. It's what we call the hydrophobic effect. So, when you have this molecule in water, as you allow the system to evolve, the molecules come together, but they come together with their fluorine atoms pointing to each other. And that's just what you see in form 1. So what's driving the formation of that first form is what's happening very early on as the molecules begin to come together, and that's driven by the way in which the molecules interact with the solvent. Now let's look at nitromethane. Here it is. It actually doesn't interact with the surrounding molecules at all much. Nitromethane doesn't particularly interested in interacting with this molecule, and so the molecules interact with themselves. And you can see at the top, you see those two dotted lines bringing these molecules together, and that's just the feature that we saw in form 2, and form 2 grows out of nitromethane. So again, what's happening really, really early on is driving the polymorphic outcome. So what we've shown here is we understand why you get these different polymorphs, and they depend on what's happening in the solvent. Now, fortunately, I have to skip the last 3 slides. I just want to say that of the chemistry part of this talk, Lots of different people have contributed, many thanks to them, and we've been well funded by a number of agencies. I'll stop at that point, but I hope I've given you some glimpse into the way in which the power of modern computers is used of material.
Modeling and to actually do anything serious. So where else in chemistry, actually, there is not enough power to.
Sorry, you're referring to the use of computer modeling in biomolecular modeling. Mm-hmm. I mean, there is a huge, that's not my area and I didn't have time to talk about it, but it is a hugely important and very active area of the field. Essentially, using the same kind of techniques that people like me use in modeling materials, people use those techniques in modeling complex biomolecules, proteins, DNA, and interactions between molecules. I mean, there are huge challenges intrinsic in the complexity of the structures that they're looking at. One of the other major, I say it's not my area of expertise, but I know that one of the other major areas of challenge for computational modeling of those systems is understanding the interaction between the molecules and the solvent. I mean, I just alluded to that topic at the end when I was talking about our fluorouracil. But it's important in certain areas of materials modeling, absolutely crucial in biomolecular modeling, and it's not at all an easy problem. But methods are very, very widely used in biomolecular modeling, as widely used as they are in the materials field that I've discussed. So thanks for that.
Actually, would you mind if I continued a little with the same question? Because I would like you to answer just a little bit further that one of the main questions about biomolecular systems is that they're often very much larger than molecules. Where do we stand these days in terms of actual computer power that's available for addressing these very large-scale, multi-scale problems?
Well, we stand actually in pretty good shape. I mean, one of the aspects that has made this field so exciting to work with over my career has been the exponential growth in computer power, which still continues. So you really now can tackle very, very complex systems, systems with many thousands of atoms, even millions of atoms, using the simpler intratomic potential approach, but even with quantum mechanical methods, which really get to the heart of how the electrons behave in the system, you can now tackle large systems. So there's a great deal you can be done, and the horizons of the field continue to expand because of the growth in computer power.
We have a question here. Excuse me.
Hi, Bill Langan. You talked briefly about your work with genetic algorithms, and you skipped over the cost function, but I got the impression there was more you wanted to say about that.
Yeah, I had to skip over rather a lot actually, but there are a number of different ones you can use. You can use very simple ones, which just based in crystal structure prediction on expected coordination numbers and bond lengths, or you can use more sophisticated ones of very approximate estimates of the lattice or cohesive energy. And we've used both in the type of work I was describing. But I mean, you're absolutely right. The choice of cost function in the GA approach is absolutely key to its efficacy.
Okay. One last question then.
Would the development of the computational models be detrimental to the development of analytical solutions to some of these problems?
Well, one should use analytical solutions when you can. There's no conflict between computer modeling and analytical solutions. We use computer models when the systems are of that complexity, which the ones I was talking about, one cannot use analytical models. You may be able to use analytical models for some of the very broader features, but if you want to get into the details, for example, if you want to do the kind of predictive work that Alpha did, calculating those temperatures in the Earth's core, you need this kind of sophisticated simulation method. But analytical models, these aren't a replacement for analytical models. Analytical models continue to be of great importance.
I think we should close now because there's a class coming in. Let's thank Professor Catlow once more.